Great. My name is Sophia. I'm a PhD candidate at UW-Madison, and my research focuses on trying to understand how we can look at lake ecosystems using new hyperspectral remote sensing technologies. So if any of you are not super familiar with remote sensing here, just for some background, most of our current and past satellites have been multispectral. So this means that across this range of wavelengths here, we only have several bands. And these bands each cover a range of those wavelengths. When we have hyperspectral instruments, which are upcoming and new on some satellites, we now have hundreds of bands across this range of wavelengths. And those bands are at now smaller increments. So if we think about this as reflectance data that we can use for our environmental analyses, we're only going to have 10 or so points along our spectra here with multispectral data. Okay, but with hyperspectral, we have a nice contiguous line spectra here, so we can see smaller differences, in my case, in lake color across time or space. So to kind of prep for what we might be able to do with the upcoming satellite data, we conducted an airborne campaign over Lake Mendota in Madison, Wisconsin. My crew on a boat zipped around Lake Mendota. You can see this with the blue line to 12 different sites, taking samples and measurements related to water quality. And then at the same time, we had a plane flying overhead the lake with two high-specs cameras mounted. And these cameras covered the 400 to 2500 nanometer range of wavelengths. All right, and we ended up with 14 events of paired in situ and hyperspectral data, ranging from March 15th to November 7th in 2024. So really trying to capture that whole season when there's no ice on the lake. And you can see some color differences as we move from March, when the water appears dark and was more clear, and then we get this lovely shade of green by September when there's a lot of phytoplankton growth. You might also notice some very slight spatial differences, especially in this northern section of the lake. This is where the Yahara River flows in, and with it, sediments and nutrients and precipitation from upstream. So we see both temporal and spatial variation, and we're hoping to see whether we can capture this just as well with our hyperspectral data. So let's choose just one of our water quality variables to start with. We'll use chlorophyll, because that's often looked at in lakes. And a simple thing that we can start with is to see at which band the reflectance is most correlated to our chlorophyll measurements over space and over time. This happens to be around 730 nanometers for chlorophyll, with an R-squared of 0.42 for that correlation. This isn't great, and we're not expecting it to be that great, because we know that a spectra of chlorophyll, whether reflectance or absorbance, has multiple important wavelengths that we should look at. So let's try adding one more band. We can use normalized difference indice equations. These often make use of one band in which the variable absorbs strongly and one band in which it reflects strongly to kind of capture that contrast. The most common one that you've probably heard of is NDVI for vegetation. But we can apply this equation to every possible two bands that we captured with our hyperspectral airborne campaign. And so if we do that, we get this histogram of our squared values up on the plot there, and you can see that we didn't improve much from just the single band prediction power. So especially with hyperspectral data, we have 100 plus bands, and we really want to try to use all of that valuable information contained there. So we then took 124 bands from our visible range and used partial least squares regression. And using this, we ran this 200 times, each with a different randomized testing set across our sites and our time events of sampling. And then we take the average of all the predictions for a given sample and plot them over here. And now we have an R-squared of 0.83. So a lot more powerful in predicting chlorophyll. And this is true for a lot of other variables that we measured as well. So you can see these are 4 optically active variables in the lake on your right. And then PLSR models show strong predictive power also for like a summative water quality measurement like Secchi depth. This is a measure of clarity, as well as a non-optical parameter like nitrogen and other nutrients as well. And so this was like looking at predictive power of single variables alone. I am also interested in seeing if we can take our hyperspectral data and actually look at like overall biogeochemical states of the lake, especially over time. So North Temperate lakes go through different seasonal phases. And this phenology can be described by the phytoplankton abundance and composition at any given time. So starting with winter, we have ice cover, so not a lot of light getting into the lake, and the water is cold. So there's not much for phytoplankton growth at this point. But as temperatures warm and the ice starts to melt, algae that can still tolerate some of the cooler temperatures start to increase as light availability increases. And we have 2 plots here. This one is showing the ratio of phycocyanin pigment to chlorophyll. Phycocyanin is only found in cyanobacteria, and those are often what we're concerned about when we think about harmful algal blooms. Meanwhile, chlorophyll is found in all phytoplankton, so that's in both cyanobacteria and in algae. So during the spring phase, we can see that the ratio is below 1. And so we know that of the phytoplankton in the lake, most of it is algae rather than bacteria. And then our Secchi depth here is a measure of clarity. Just note the inverted y-axis. So this is us measuring the clarity by watching a disk that we lower into the water. And as soon as we can't see it, we take a measurement. So when the line lowers is when the water column is more clear. So speaking of clarity, in Lake Mendota, when we hit around May, there's a phase in which our Secchi depth is greatly increased. And this is because zooplankton are very abundant. These are Daphnia in this video here. And they are munching away at all the phytoplankton and clearing it out of the water column. And eventually those zooplankton kind of hit their peak abundance and they start to decline. So making space for phytoplankton to grow again, and the water is also warming up significantly. And there are still nutrients available. And this makes way for cyanobacteria to dominate kind of through the rest of the ice off season on a lake. And so we see now that that phycocyanin to chlorophyll ratio is usually above 1, so there's more cyanobacteria than algae now. And our Secchi depth is back to being a lower depth, so less clarity because there's more bacteria in the water column. All right, so our field campaign spanned these different seasonal phases, and we were collecting 2 sets of data, really. One set being the hyperspectral, so reflectance at hundreds of wavelengths, and then the other set being our in situ data, biogeochemical water quality variables. And let's subset that down to just the visible wavelengths and just our visible water quality variables. And we ran a canonical correlation analysis. This is similar to a PCA, but we have 2 separated sets of data. And it's finding linear combinations that maximize correlation between those 2 subsets of data. So in this new 2-dimensional space, these points here are our hyperspectral data. at every sampling point across space and the sites in our lake. And if we color these by date, we see that there's a pattern, and they're quite clumped that way. And then I went ahead and drew circles over these dates that match with these different seasonal phases. And it's really exciting to see that this CCA is able to distinguish quite well between these different seasons. And the cool thing about CCA is that we can also then look at the drivers, from either set of data. We can take the drivers and look at how they influenced the creation of these two new axes. So I went ahead and plotted the drivers for our 4 optically active variables. The length of the arrow is just like the strength of that impact on the created axes. And we can see that the location of these different seasonal phase circles really makes a lot of sense with what we see here. So canonical variant 1 is able to kind of separate out algae in the spring from cyanobacteria later in the season. And then canonical variant 2 is separating out clearer water from water that is more turbid with phytoplankton present. And this is a really exciting plot to get, and I think it really makes me optimistic that rather than just single variables, we can also use these information-dense hyperspectral data to look at lakes at a more ecosystem level. And with that, I'll just thank all my collaborators at UW-Madison. We're coming from all different departments and centers. If we have time, I can take questions, and I'll also be at a poster this afternoon if you want to chat more.